just for reference, we're on page 59 in our note packet. And before we move on to new material, let's do a quick review of our previous material. You can see a quick note or two at the top here I've written. So before the break, we were speaking about sampling distributions, and specifically sampling distributions of X bar. Remind yourselves what X bar means. It's the mean or average of some data we have collected. We had this idea that if I collected a data set, Joey collected a data set, Sally collected a data set, we all found the means of our data sets. They're going to vary from our 3 different samples because we have different subjects in our data sets. It's important for us to know what our different sample means are going to look like if we're using them to make predictions about mu, the mean for the whole population. So, the central limit theorem gave us this very useful result. You'll see on the right-hand side, we wrote down X bar, the mean of the data, and we said the mean of the data is going to vary from sample to sample. We had this little tilde, meaning it can be modeled by all these different X bars. Capital N told us it can be modeled by a normal distribution, that bell curve. Never plug in a number here. It's telling us the different sample means look like a bell curve if we have a decent sample size. And that bell curve is going to be centered at mu. Remember, mu is the population mean. So even though myself, Joey, Susie, we're all going to get different means, they're going to be centered at that same spot, that bullseye, the mean of the whole population, the thing we're trying to estimate. And then we also need to know how much our different samples are going to vary by. So that's our last term, sigma, the original standard deviation, divided by the square root of n. So you'll notice here that as n, our sample size increases, the variability from data set to data set is going to decrease. This last term we've called the standard error of the mean. So it's just a fancy way to say, here's how much my statistic, the sample mean, is going to vary from sample to sample. All right, so this sampling distribution of the mean deals with quantitative data. Remember, that's numerical data, so if I'm talking about age, height, length, stuff like that, it makes sense to talk about average age, average height, average length. What if I have categorical data? So we're moving on to categorical data. So for example, the major of everyone in the class. Makes no sense to talk about the average major. What I could talk about is proportions, though. What proportion of students are marine science? What proportion of students are psychology majors? And so on. So categorical data, we're going to be talking about proportions instead of averages. And for context, we're going to be looking at some information from the National Safety Council, and we have this information that 28% of all traffic crashes are due to drivers using their cell phones. Just an encouragement, get off the phone when you drive. So 28% of all traffic crashes due to people being on their phones. Maybe we're looking at legislation to help with this fact. Instead of looking at every single traffic accident in the U.S., let's take a look at a sample of 200 accidents and study those to inform us on legislation. So let's revisit some familiar terminology here, but now in the context of categorical data and specifically proportions falling in proportion of observations falling into different categories. So in the context of our example, we have our population distribution, and here we're going to use the notation P, and this is going to represent the proportion of all, emphasizing all here, accidents due to phones. Okay, and they tell us in this problem that the value of P is 0.28. So much like we have mu to represent the mean of the whole population, we're going to use the symbol P to represent the proportion for the whole population. And we're given for this particular problem, that's 0.28. Now let's check out our next piece of terminology, the data distribution. So instead of looking at everybody, we're going to take a sample instead, and look at an estimate from the sample. We're going to change up our notation to make it really clear what we're talking about. So here we're going to use p hat to represent the proportion in our sample. And sometimes we might use that notation as x, how many were due to people being on their phones, over n, which in this case would be 200. I'm taking a sample of 200 accidents. So again, much like we had mu for the whole population and x bar is the mean for the sample, we've got p, the proportion for the whole population, versus p hat, the proportion for our data. Now we have this same concept. If I look at 200 accidents, I might get 27% due to cell phone use. If Joey looks at 200 accidents, he might get 30% due to cell phone use. Susie looks at 30 accidents, she might get 35% due to cell phone use. So we need to take a look at this idea of how our statistics, our p hats, are going to vary from sample to sample. So sampling distribution, this tells us how the sample proportions, and remember our new notation for that, p hat, vary from sample to sample. And in our particular setting here, we're going to write this a similar way we did for means. We're first going to jot down p hat to say this is our statistic. We're going to say can be modeled by, so we're going to use this little tilde. Again, representing I take a sample, you take a sample. We get different statistics, different sample proportions, and we're going to explain what they can look like. If you take a wild guess at the shape, you can probably figure out what I'm about to write down. N, again, meaning these are also going to follow a normal distribution. So hopefully you're getting a sense of why z-scores are so important now in the normal distribution that we've been working on for a while. So p hats are also going to be normally distributed. And where are they going to be centered? Where would it make sense? X bars were centered at mu, the population mean. Similar concept here. P hats, the proportions from the data, are going to be centered at p, the proportion for the entire population. And then we also need to think about how much they're going to vary by. This term, square root of p times 1 minus p over n. All of that is under the square root. The second term here, we're going to call our standard error of p hat, again representing how much the proportion is going to vary from sample to sample. Now, just as a final reminder up here for the normal distribution, we said this kind of applies when n is at least 30. Then we can say the means are going to have that normal shape or normal distribution. For proportions, we also need to have a sample size criteria. And jot that down here. So this is going to apply when n times p, and if you think about that in plain English, this is telling us how many successes are expected. Okay, so number of successes expected is at least 10. So we have at least 10 successes expected. And then similarly, I'm going to emphasize here, I'm going to say and. Need both of these to be true. N times 1 minus p is at least 10. So if I have a p chance of success, then 1 minus p is my chance of failure. So n times 1 minus p means at least 10 failures expected. All right. This closes up kind of the introduction. I'm going to get started on an example in the next video, and then we're going to let you guys try a problem on your own.